For centuries, Mars has occupied a strange space in the human imagination. Close enough to see with the naked eye, yet distant enough to remain mysterious, it has been a canvas for speculation, myth, and eventually science. Early astronomers mapped faint lines across its surface, believing them to be canals. Writers imagined civilizations clinging to survival on a dying world. But today, the story of Mars is no longer written in guesswork. It is written in data, collected painstakingly by orbiters, landers, and rovers that have transformed the red planet from a distant curiosity into one of the most studied worlds in our solar system. We now know Mars is a planet of extremes and contradictions. It hosts the largest volcano in the solar system, Olympus Mons, towering nearly 3 times the height of Mount Everest. It contains Valles Marineris, a canyon system so vast it would stretch across the entire continental United States. Its surface bears unmistakable scars of ancient rivers, lake beds, and perhaps even oceans, clear signs that liquid water once flowed freely there. Beneath its dusty crust, vast reserves of ice remain locked away, preserving a frozen record of its past. And yet, despite all we've learned, Mars continues to surprise us. Because sometimes, the most important discoveries aren't the ones we set out to find. Recently, a subtle, almost dismissible signal, something so small it could easily have been ignored, may have revealed one of the most elusive phenomena scientists have searched for on Mars for decades. Not a dramatic image, not a sweeping geological feature, but a sound. A tiny crackle. The kind of sound you might hear when unplugging a cable from a speaker. Brief, sharp, easy to overlook. But in the thin, quiet atmosphere of Mars, that sound could represent something extraordinary, the first direct evidence of lightning. And if that's true, it changes more than you might expect. To understand why this matters, we need to go back to the beginning of Mars exploration. In 1976, humanity achieved a milestone that redefined planetary science. 2 robotic explorers touched down on the Martian surface for the first time. These missions provided the first true close-up look at an alien world. The images they sent back revealed a barren, rust-colored landscape under a hazy sky. No cities, no canals, just rock, dust, and silence. But that silence was deceptive. Over the decades that followed, mission after mission expanded our understanding. Orbiters mapped the planet in exquisite detail. Landers studied its soil. Rovers roamed its surface, drilling, sampling, and analyzing everything they could reach. Today, 2 robotic explorers continue that legacy. They traverse the Martian terrain, acting as our eyes, ears, and laboratories millions of kilometers away. Through them, we've learned that Mars was once far more Earth-like than it is today. It had a thicker atmosphere, stable liquid water, and conditions that may have been suitable for life. But there's one thing scientists have been searching for, unsuccessfully, for a very long time. Lightning. On Earth, lightning is so common, we rarely stop to think about it. A flash in the sky, a crack of thunder, a passing storm. But lightning is far more than a visual spectacle. It is a fundamental process that shapes planetary atmospheres. It begins with motion, tiny particles colliding within clouds. On Earth, these are usually ice crystals. As they bump into each other, they exchange electrons, becoming electrically charged. Over time, this creates a separation of charge, positive in one region, negative in another. Eventually, the imbalance becomes too great. The air, normally an insulator, can no longer hold back the growing electric field, and in a fraction of a second, the system corrects itself. A bolt of lightning tears through the sky. In that instant, Temperatures soar to tens of thousands of degrees. Molecules are ripped apart and recombined. New chemical compounds form. Energy is released on a massive scale. Lightning helps drive the chemistry of Earth's atmosphere. It contributes to the nitrogen cycle, producing compounds that fertilize soil. It generates ozone, which helps shield the planet from harmful radiation. Some scientists even believe lightning may have played a role in the origin of life itself, triggering chemical reactions that led to the formation of complex organic molecules. In short, lightning isn't just weather, it's a planetary force. So naturally, scientists have long wondered, does lightning exist on Mars? At first glance, the answer seemed like it should be no. Mars has a very thin atmosphere, more than 100 times less dense than Earth's. It lacks the thick cloud systems where lightning typically forms. It doesn't have the same kind of weather dynamics we see here, but Mars does have something else. Dust. Lots of it. The surface of Mars is covered in fine, powdery material, and when the wind picks up, that dust doesn't just move. It comes alive. It swirls into towering dust devils that can reach heights of several kilometers. It gathers into regional storms that can span continents, and occasionally, those storms merge into something even more dramatic. Global dust storms that engulf the entire planet. These storms are unlike anything on Earth. They can darken the sky for weeks or even months. They can shut down solar-powered spacecraft. They can reshape the landscape itself. And crucially, they create the perfect conditions for electrical activity. Because when dust particles collide, just like ice particles in Earth's clouds, they can become electrically charged. In other words, Mars may not have storm clouds filled with ice, but it does have storms filled with dust. And that might be enough. For decades, scientists have tried to detect lightning on Mars. Orbiters scanned the atmosphere for flashes. Instruments searched for radio signals associated with electrical discharges. Specialized missions were even designed specifically to measure atmospheric electricity. Again and again, the result was the same. Nothing. No flashes, no signals, no definitive evidence. It was as if Mars refused to give up this particular secret. Until now. The breakthrough didn't come from a lightning detector. It didn't come from a dedicated atmospheric experiment. It came from a microphone. One of the most advanced instruments currently operating on Mars includes a system designed to analyze rocks. It uses a laser to zap the surface, then studies the resulting light and sound to determine chemical composition. As part of this system, a microphone records the acoustic environment. Its job isn't to listen for storms, it's to listen for rocks. But in doing so, it also listens to everything else: wind, movement, vibrations, and occasionally something unexpected. While reviewing data collected over many months, scientists noticed a pattern. Short, sharp acoustic signals, pops, crackles, tiny bursts of sound. At first glance, they didn't seem important. They could have been anything: instrument noise, mechanical interference, even dust hitting the microphone. But they kept appearing. And more importantly, they appeared under specific conditions. Most of them occurred during dust activity, storms or dust devils. That correlation raised a question. What if these weren't random noises? What if they were signatures of something physical, something electrical? To test that idea, researchers began a detailed analysis. They examined the timing, frequency, and characteristics of each signal. They compared them against known sources of noise from the rover itself. They ruled out mechanical explanations. They considered environmental factors. Then they took it a step further. They recreated Martian conditions in a laboratory on Earth. Using similar instruments, they generated static electricity by agitating fine particles, essentially simulating a dust storm. They recorded the resulting signals. The comparison was striking. The lab-generated signals closely matched the mysterious pops detected on Mars. Not perfectly, but enough to suggest a strong connection. Enough to propose a bold conclusion. These sounds may be the result of electrical discharges in the Martian atmosphere. Not large, dramatic bolts of lightning like we see on Earth, but small, rapid, static-like discharges. Tiny sparks. At around the same time, another piece of evidence emerged. Scientists analyzing data from an orbital spacecraft discovered a rare type of radio signal known as a Whistler wave. On Earth, Whistler waves are closely associated with lightning. They occur when electromagnetic energy travels along magnetic field lines, dispersing in a characteristic pattern. They are, in many cases, a fingerprint of lightning activity. Finding one on Mars was unexpected, because Mars doesn't have a global magnetic field like Earth. Instead, it has localized magnetic regions, remnants of an ancient field that disappeared billions of years ago. For a Whistler wave to form, conditions have to be just right, and yet one was detected. Just one. Brief, fleeting, easy to miss. But combined with the acoustic evidence from the surface, it strengthens the case. Individually, each signal might be dismissed. Together, they tell a story. So what does this mean? If Mars does experience electrical discharges, even small ones, it has major implications. First, it changes how we understand Martian weather. Electric charge can influence how dust behaves. Charged particles are more easily lifted by the wind. They can clump together or repel each other. They can alter the structure and evolution of storms. In other words, electricity may not just be a byproduct of Martian dust storms. It may help drive them. Second, it offers a potential explanation for a long-standing mystery. Mars is rich in highly reactive chemicals known as oxidants. These compounds can break down organic material, making it difficult for scientists to detect signs of past life. For years, researchers have debated how these oxidants form. Electrical discharges provide a plausible mechanism. Even small sparks can break apart molecules and trigger chemical reactions. Over time, these processes could produce the oxidizing compounds observed across the planet. If that's true, it has profound implications for the search for life, because it means the Martian surface may be far more chemically hostile than previously thought. Any organic material exposed to the surface could be rapidly destroyed or altered, which means if life ever existed on Mars, its best preserved traces are likely hidden underground, protected from radiation and chemical activity. There's also a practical side to this discovery. Future missions to Mars, especially those involving humans, will need to account for electrical activity. Even if Martian lightning is weak, it can still interfere with equipment. Static buildup can affect electronics. Charged dust can cling to surfaces, coating instruments, degrading performance, and reducing efficiency. This is already a known challenge. Dust accumulation has ended missions before. Add electrical charging to the mix, and the problem becomes more complex. Engineers will need to design systems that can withstand not just dust, but electrically active dust. Spacesuits, habitats, vehicles, all of them will need protection. Because on Mars, even the smallest spark can matter. And perhaps that's the most fascinating part of this story. Not the scale of the discovery, but its subtlety. A tiny sound, a brief signal, something that could easily have been overlooked. yet within it lies a deeper understanding of an entire planet. It's a reminder that exploration isn't just about big moments. It's about paying attention to the details, because sometimes the universe doesn't shout its secrets. Sometimes it whispers. Mars is still a world full of mysteries. We've mapped its surface. We've studied its atmosphere. We've walked its terrain through machines. But we are still learning how it works, still uncovering the processes that shape it. Still discovering that even after decades of exploration, it can surprise us. And somewhere out there, on that cold, dusty world, storms continue to rise. Dust continues to swirl. Particles continue to collide. And in the midst of it all, tiny sparks may flicker, unseen, unheard by human ears, but captured by the instruments we've left behind. Signals from a planet that is far from silent. The question now isn't just whether lightning exists on Mars. It's how much of it there is, how it shapes the planet, and what else we've been missing. Because if a single crackle can reveal so much, what else is waiting to be heard?